Hi everyone, welcome to week 7. Week 7 will be looking at the confidence interval, confidence levels, 90%, 95%, um, significant level, alpha equal to 0.1, 0.01, 0.05. So confidence level and the significant level can be calculated as confidence level equals to 1 minus alpha significant level, or alpha equals to 1 minus confidence level. Okay. Then calculation of confidence interval. Calculate the CI confidence interval when the population variance sigma square, or the population standard deviation sigma, is known. And calculate the confidence interval when the population variance is unknown. When the population variance sigma square, or the standard deviation sigma, is known, we will be using a z-score, use z distribution as a sampling distribution to calculate the confidence interval. When the population variance is unknown, then we will be using the sample variance and the sample standard deviation to estimate the population variance and standard deviation. In this case, we will be using a t distribution to represent the sampling distribution instead of z distribution to calculate the confidence interval. Okay, so again, we do a quick recap. Statistical inference is about using a sample to estimate something, typically like a mean value about the population. Okay, so population is the mean is our target, the population mean, which is unknown. Okay, ID, then interval estimator for population mean. So if the random variable is a continuous variable, if a random variable is a continuous variable, then since the sample space is infinite, so for any mean value, say the average height, so the height can be 7.33. What is the probability for 7.33 C 173.33 cm to be the average height of this cohort of student? Then the chance is actually zero, because you have only one point estimate, 173.33, divided by the number of samples in the sample space, which is infinite. So any number divided by infinite number of sample space will result at a zero probability. So theoretically, there will be zero. Then that's why we need to have a interval for continuous random variable. So if it's 1.33 plus minus 3 centimeter, then the alpha is 3 centimeter. Here, yeah, alpha is also called, from now on, we'll call it a margin of error, ME. Plus minus this margin of error, then how many number of real numbers within this range? Then there'll be infinite. Okay, so infinite divided by infinite, then it's bounded, then you can get a finite probability. So that's the reason we need to use a interval to estimate. Okay, how many steps per day? So there is a few examples. Then we say alpha is a margin of error. Okay, x bar n is the sample mean, n is the sample size. Okay, how many samples are being collected? And that's n samples. Then for these n samples, let's calculate the average value of these n samples. So this x n bar, then plus minus a margin of error. Okay, so when the interval estimate contains the unknown population parameter, unknown parameter mu, population mean, at least p% of the time, we call it, this is the interval estimator, a p% confidence interval for mu, population mean. So assuming we are collecting the sample n equal to 30. So again, we collect 1,000, 10,000 samples. If we collect 1,000 samples, then out of these 1,000, if we set P to 90% of confidence, so out of this 1,000, 1,000 times 90%, you will have 900. Okay, so we actually have 1,000 confidence interval constructed because each sample will you can construct a confidence interval, and it vary a little bit because of the samples. Each sample are different out of these 1,000. So we have actually 1,000 these samples. So when we have 1,000 these samples, we will expect 900 sample confidence intervals will contain the true population mean in the middle. Then there will be about 10 will be off, not be able to contain that population mean. So this is the one shown here. Okay, so here is an example that uh, you construct a k number of confidence interval. Now here is k equal to 100, so we have about 100, and you have a true population mean are centered at mu. So mu is 173 centimeter. Okay, so you have collected 1,000 samples. Each sample contains n measurements, sample size n. You have 100 sample means, then 100 uh, confidence interval. But each of them will vary around this mu value. So if we are achieving a 99% confidence level, then out of these 100, we expect 99 of these 100 interval CIs, confidence interval, will actually make sure the mu is within this range, and maybe one of them is off. So this is the concept of the confidence interval. Okay, P% confidence interval. So assuming we have a lot of samples being collected, and for each sample we can construct one confidence interval. Then out of so many confidence interval, we have P percentage of those confidence interval actually contain the mu value in the range. Okay. Okay, so margin of error. Okay, margin of error. So yeah, this is again, so for one sample that you collected, then you can construct the sample mean plus minus the margin of error. Then the true population mean is assumed at 5K number of average fish. Then whether this interval will actually contain the 5K in the middle. Okay. Sometimes it is, sometimes it's off. Say, for example, if your sample mean number of fish being caught from one ship fishing trip is about 4K, then based on the sample, you find the margin of error that can be calculated plus minus 500. You find this particular confidence interval, the 5K is actually outside of this range. Okay. So 6K plus minus 500 as well. So, okay. So for CF confidence interval for mu, when the population variance is known, sigma square is known. Okay, so how to find the right value of alpha, alpha margin of error to get a 90% confidence interval. Okay, so we'll look at how to calculate that one. Okay, here is the example. So two margin of error, that is area. So we make sure that this sampling distribution, so the red curve is the sampling distribution. So how to calculate the sampling distribution? Based on last week, we can find the sampling distribution first is a normal distribution. The mean value of the sampling distribution is the mean of the sample that you are collected. Then the deviation or the variance of the sampling distribution is the variance of population divided by the number of sample n. N, right? N. So yeah, that's the one. Divided by 50. The sample size is 50. X bar 50, 50. So okay, so once we have constructed this normal distribution, then we want 5% on the left tail and 5% on the right tail, we can find what is the range. Okay, so that's the rationality. Yeah. So there'll be some techniques over there. Techniques then is saying that for the probability, f is the CDF, right? It's a CDF cumulative density function. So we want a value to be equal to 0.95. Then what is this alpha? So one side is 5%, 2.5%, another is 2.5%. You want to achieve a 90%, then you will find 5% to the right and 5% to the left. Then the area up to 95. There are 5% plus 90 in the middle. Then what is that value there? Then do a few calculation and conversions, you will be able to find that this formula, okay? So alpha or margin of error equals to the critical value, times the uh, square root of variance divided by sample size. Okay, this one is equivalent to the standard deviation divided by square root of n. So the standard deviation divided by square root of n is called standard error. Standard error. Standard error is the standard deviation of the sampling distribution. So so far we are here. Okay, so there will be a few nitty-gritty of the R calculation. So I'll get back in a short while. Okay, so now look at here. Recall last week that central limit theorem. Okay, so what you are seeing here on this curve, this is a what it is? It is a population distribution, sample distribution, or sample distribution of the mean. How do you determine that? Okay, you observe this chart, you observe this curve. The element under it to form this distribution is our x bar. So see, x1 bar, x2 bar, xk bar. Right? So x bar is a mean value. It is not the original measurement of any of the population, but it is aggregated value. It is mean value. So it is the distribution of sample means. So this is a sampling distribution of the mean. Okay, so there's k x bars. Each x bar is a average of n samples collected from the population. Okay, so n is at the meantime unknown. Okay, unknown to you. So this particular distribution, let's say for x1 bar, it has n individuals, n samples. So for this S1, sample 1 that we are collected, we can calculate x bar 1, right? We can also calculate the standard error and the confidence interval for that particular sample. So now the standard deviation of this sampling distribution is called the standard error. It's called the standard error. Okay. Standard error. So if the population standard deviation or variance is already known to you, in the question or in the real world, it's already known to you, then theoretically the standard deviation of the sampling distribution, again, can be calculated as standard error divided by square root of n. Recall last week, we are talking about the variance of the sampling distribution, right? We say the variance of the sampling distribution is equivalent to the population variance divided by n sample size. So two sides, both sides, left-hand side, right-hand side, you get a square root. You get the standard deviation of the sampling distribution is the standard deviation of the population sigma divided by square root of n. Okay, this is when your sigma is known. Okay, when sigma is known. When the sigma is not known, then what to do? Then you need to use the sample's standard deviation, to approximate or simulate or estimate the sigma. So we do not know the sigma, but we only know the S. How do you get S? S you can calculate based on one sample. In most of times in practice you only have one sample. So here in this example, you have S1, S2 till Sk. You have 100 sample means. Okay. But in reality, most of times you will only have one sample mean, which means you only have one sample. One sample, you have n measurements, n individuals that draw from the population. Then for this n, let's say n equal to 30, so I assume 30, there are 30 individuals, right? So out of these 30 measurements, we can find the sample standard deviation. We can find the standard, which is written as S. Okay, so S is the standard deviation of the first sample. Okay, so then the standard error or the standard deviation of the sampling distribution can be calculated as divided by square root of n. Okay, so these are the key things here. Then next is we are going to calculate the critical value. Okay, critical value CV or Z-score or T-score is based on the confidence level that we want to achieve. Confidence level is called CL. Confidence level can be 90% or 95%. Then significant level alpha. Here is another alpha. That's why I will try to avoid alpha in the early place. We call it margin of error. Okay, so significant level is from 0.1, 0.2. So confidence level is 1 minus significant level. Okay, then margin of error is calculated as critical value at certain confidence level, P percentage, or at alpha. Sometimes we write both ways. Alpha equal to 0.01, that means 1%. 1%. Then significant level will be 1 minus 1%, 99%. Then times SE. SE, the standard error or the standard deviation of the sampling distribution. So you always remember this magic formula. Margin of error equal to critical value times standard error. Okay, then the confidence interval is quite straightforward. Confidence interval is X bar, which is a sample mean. If you have one sample of n elements, then sample size n, then you calculate one X bar plus minus this margin of error, which is equivalent to X bar plus minus critical value at alpha significant level or critical level at or critical value at CL confidence level, P percentage, time the standard error. Okay, so this is the magic formula. With that in mind, later we'll look at the examples. Okay, so later we'll introduce this T distribution, when to use T distribution, when to use Z distribution. So when the sigma is known, use Z distribution. When the population standard deviation is unknown, you can only use sample standard deviation, then you use T distribution. Okay, the T distribution. This actually goes to here. Okay, so in order to find what distribution to use to calculate the critical value, because the critical value is attached to the underlying distribution that you want to use, whether it's a Z distribution or a T distribution. Okay, so first you check the data that you have, the problem that at hand is the sigma known to you. If it's known to you, population standard deviation known to you, then you ask yourself, is the population known to be normally distributed or not? If it is, you go use the distribution straightforward. If it's not a normal distribution, build it or you are not aware, you're not sure, then you check the sample size. If a sample size is greater than 30, Z distribution, not greater than 30, then you will require more data. But in very rare cases, you are forced to calculate, even if it's in this bucket, then you use T distribution. But this is a rare case. You should use T. That's a fallback plan. So if the standard deviation of the population is not known to you, it's unknown, okay, then we'll use S, the sample standard deviation, to approximate the sigma, okay? Then you ask, is the population normal? If it's known to be normally distributed, then you use t distribution straight away, okay? There's no more z distribution around this area, so always t distribution. Then if it is not normally distributed, then according to central limit theorem, you want the sample size to be large enough so that the sampling distribution can be a normal distribution. Because the population distribution is not normal. If the population distribution is normal, your sampling distribution will be normal, even your sample size is small. But if your population distribution is not normal, then in order for your sampling distribution to be normally shown and displayed and formed, then you need a sample size to be large. So this is the rationale behind. Okay. So if the sample size is greater than 30, then use t distribution again. If it's not larger than 30, then you need more data or use simulation. So these are the key things for key theories behind confidence interval. Okay. Then we look at 7.2 application of confidence interval. Then here is again confidence interval is calculated as x bar n, sample size n, minus plus something, this complex thing. So the ZP prime is the critical value CV. Then the sigma divided by square root of n is the standard error or the standard deviation of the sampling distribution when sigma is known. When sigma is known, we use Z distribution. That's why it's called a Z-score, okay? So CV times standard error is your margin of error. Next is when we are going to use t distribution, okay? When the standard deviation of the population is not known, then we use S divided by square root of n as the standard error. And that's the time the critical value, in order to calculate the critical value, then we need to use a t distribution. Okay. Then it becomes a t-score times the standard deviation of the sample divided by square root of n. So if the population standard deviation is not known, then we'll be using t-distribution. Okay. Okay. So yeah, so this is the example that you can run R to look at that. So here is again that if X is normally distributed, then if sigma is known, use Z and sigma. If sigma is unknown, use T and the standard deviation of the sample. Okay, so what if X is not normal? So yeah, that's the scenario. Actually, I already showed you earlier with the decision tree. Okay, so there'll be examples. Yeah, what if X is not normal and the sample size is small? Then you need to collect more data. In general, collect more data. Yeah, so that's a theory part. Next is we are going to look at the tutorial. Okay, tutorial. IQ tests are designed to yield scores that are approximately normally distributed. Okay, they already tell you the population is normally distributed. Then a reporter gathers the IQ score from 22 employees. So it is small, but it's okay. It's already tell you the population is normally distributed. Sample mean of this one, X bar 106, N equal to 22. She assumed the population standard deviation is known to you sigma 15, then compute 95% confidence for the average. IQ in this firm, 99% confidence interval. So first, you determine whether you should use Z distribution to calculate the critical value or you use the T distribution, okay? So we follow this decision tree, okay? First, is the population sigma known to you? Yes, already tell you it is known to you. Yes, it's known to you. It's 15, right? So 15, go down. Is the population normal? Is that population normal? Okay, you go straight down the distribution. Okay, the distribution. But remember how to calculate margin of error. Margin of error is critical value, Z distribution or T distribution at confidence level times the standard error. So in order to calculate margin of error, we need to find the CV and the standard error. Okay, so now next. First one, let's start with this. First, use this distribution and this score. Okay, for 90% confidence interval, we need to find the z-score. Okay, how to find the z-score? 90% confidence interval z-score. Yeah, so this is the one. So Z distribution, Q norm. Q norm. First, P equals to how much percentage of confidence we want to achieve? 90%. 90% means that's a bell curve, left tail 5%, right tail 5%, right? So Q norm is going to give you the cutoff score, which is the Z score, at a certain probability up to this from the left, negative infinite to the probability from 0 to up to 0.95, so 5% at the tail. Okay, in fact, the mean value and the standard deviation you do not need because it is standard norm. So it's going to give you this score 1.64. Okay, 1.64. So this is the z-score, or called the critical value. Critical value at p%, which is 90%. Critical value of 90%, so 1.04. So we can have z 95 is 1.64. Okay, so margin of error equals to the z-score critical value times the standard error, right? So what is the standard error? Standard error is the population standard deviation divided by square root of n. So population standard deviation is 15 divided by SQRTN. N equal to 22. Okay, so this is your SC. That will run it. So SE is 3.19. Okay, then next thing, margin of error is the critical value times the SE. So you have this margin of error 5.26. Then your lower bound is your X bar 106 minus the ME. Okay, then your upper limit is your 106 plus ME. Okay, so let's try look at that. So lower bound, upper bound. So this is a way to calculate the confidence interval using z-score. Okay, because the population itself is normally distributed, known to you, and the population standard deviation are also known to you. Okay. Next is, okay, there's another approach. Okay, so you can get it right in one shot by setting the mean value and the standard deviation. Yeah, that's another way to do it. So 1.2, computing 99% confidence interval for the average IQ. So 9% confidence, that means one side is 0.05, another side 0.05. So 99 plus 0.05, so 0.995. So only 0.05 will be on the right tail side. So 1 minus 0.005 is 0.995. Okay, so this is your z-score. Z-score, z-score already told you here. Then next is margin of error. Again, always calculate margin of error is the z-score times the SC. SC doesn't change. SC doesn't change. We already have this SC earlier, right? So SC doesn't change. SC doesn't change. No, run it. SC is a 3.19. It is still 3.19. Then run it. Your ME now changed to 8.23. Okay, 8.23. So now you get this one minus ME. This one is plus ME. Front one. Okay, so upper limit, lower limit. 97,114. 97,114. Okay, in order for you to be more confident, you are noticing that you notice the confidence interval gets wider. Wider. You want to be more confident, more confident. Get wider. So from earlier 100 to 119, now it's going to 97 and 114. So it's getting wider. So wider means more coverage. I'm more likely to, when you extend the confidence interval from narrow to wider, there's more chance for the mu value, the population mean, to fall into this larger range and wider range, right? So this is reasonable. Yeah, okay. In order for you to get 100% confidence, what will happen? If we want to get 100% area under the curve, then what are the two sides of the cutoff line? It will be negative infinite to positive infinite. So that's the entire range of the real world and real number. So it is not meaningful. So yeah, you want normally nobody knows do this 100%. It's not meaningful. So, yeah, okay, 1.1. So, yeah, we have finished 1.1, 1.2. Then question 2. Let's look at question 2. In order to estimate the mean weight loss of all customers in a weight loss program, and you train the sample of 18 dieter, sample of 18, this pretty again small n equal to small, it will alert you. Any sample size smaller than 30 will actually alert you. The customer sample mean sample standard deviation. Oh, sample standard deviation is known to you, not population. Sample standard deviation of the weight loss. Sample mean and sample standard deviation already told you. Okay, very good. Then he believes the weight loss is normally distributed. That means the population is normally distributed. Calculate 95% confidence interval. Okay, so again, we go to this decision tree. Is population standard deviation known to you? Population standard deviation is not known to you. You only sample standard deviation, right? So we go here. So is the population normal? The population is believed to be normally distributed. Then you go down. So t distribution. Okay, t distribution. Even the sample size is small. So regardless of the sample size, as long as the population is normally distributed, then the sampling distribution will be normally distributed. Okay, so now we know it is t distribution. We are going to use t distribution for question 2. Question 2. Question 2 is straightforward. So first, let's have a look at QT. Okay, QT. It's a student t distribution. So dt is the PDF, probability density function of t distribution. Then pt is the CDF, cumulative density function. It gives you the probability. Qt is the inverse function. Then RT is giving me the random number. Okay, random number from. So first is margin of error equal to CV times SC. Always remember that. So we need to calculate the CV. SC first. Maybe SC is easier. Standard error is the standard deviation divided by SQRTN. Okay, S is 9.2, N is 18. Okay, 9.2. Here is 18. Okay, so let's have a look. SE now is SQRT. Oh, error. SQRT. Okay, there'll be a few error. Okay, SE now we get it 2.168. Okay, so that's a 2.168. Then what about CV? CV now this time we're using T. So we want to get a quantile. So QT. Then what is the probability that we need to key in? QTP equals to probability equals to how much confidence we want to achieve? 95. 95 means one side 2.5, another side 2.5. So 2.5, 1 minus 2.5 is 1 basically 1 minus 0.25, 2.5, 0.025. P is this value, 0.975. Then next is degree of freedom, which is n minus 1. N minus 1, what is n? N is 18. 18 minus 1 is 17. Okay, so CV, we already got CV. CV is 2.10. Okay, 2.10. Then what about ME equals to CV times SC? So now we have ME is 4.57. Okay, ME 4.57. Then next is lower bound, upper bound is easy. Then X bar is 11.5. So 11.5, I teach you a trick, plus C minus 1 plus 1, then times ME. Okay, so you get this one. Okay, you will get two values. So basically 11.5 plus minus 1 times ME, then 11.1 plus 1 times ME. So we give you these two numbers. Okay, so lower bound and upper bound. Oh, yeah. Yes, lower bound and upper bound. Please calculate as this range. Okay. So that's question 2. Then question 3. Okay, question 3. Consider the building data set chick weight in R. Consider the population. Actually, not population. You can treat it as sample. Okay. So in this, because this is data set provided to you, and it does not contain the entire population of the chicken ID on this planet. So it's actually only a sample of 10-day-old chicken where we define RV of their weight as 10, so the data of a 10-day-old chick to build a 90% confidence interval. Okay, 10-old. Okay, so question 3. First is the chick weight. So chick weight is a large number out of more than 500 chick weight. Then we say we want the chick weight to be time equal to 10. So this is one way to find the time equal to 10 days. Okay, or the check weight of time equal to 10 days. Okay, so this is one way to do it. Remember last time I also share with you a method that means use a comma, use a comma. So if you are using comma, so it will give you all 10 time equal to 10, those records are then the weight, chick, and the diet. They will show you all of them. Okay, they're all of them. Okay, now next, if you are particularly interested in weight, then what you can do is give me the weight. Give me the weight, then you will get weight. So the result will be the same as what you write earlier. The result will be the same as these. These two are the same. Okay, but you can try use a comma, then that will show you all the columns. So easier for you to verify. Okay, next is length. Again, we use a length, right? So let's have a look. Length n equal to 49. So there are 49 chicks of 10 days old. Then x bar is the mean value. So we find the mean value of it. So what is the mean value? X bar. The mean value is 107. 107 gram. Okay, 107 gram. Next is the standard deviation of this sample because we do not have population standard deviation, and the sample size is 49 is greater than 30, right? So now actually we are checking based on these samples, population standard deviation known to you? No, not known to you because it's a sample. Then is the population normal or not? We do not know the chick weight is normal or not normal. In fact, it is not normal. Then go here, sample size greater than 30. Sample size we find is 49. So sample size greater than 40, you use t-distribution. But we also want to verify this, which is the chick weight, right? So type a histogram. So these are the 49. 49. You can have a look at this 49. So yeah, I'm not very sure whether it's normally distributed or not. Look, it's actually not quite symmetric, so it might not be normally distributed. So since the population we are not sure, then we check its sample size. Sample size n greater than 40, greater than 30, then we use t-distribution. Okay. So now in order to use t-distribution, we need a we need to calculate the margin of error, right? Margin of error. Again, margin of error equals to CV times SE. What is the CV? Critical value. CV equals to QT. Then what is the confidence we want to achieve? We are at 3.1. Okay, 3.1. 3.1. We want to achieve a 90% confidence. That means 5% to each side. So probability 1 minus 5% at each side, 5%. Then degree of freedom is 49 minus 1. Yeah, so look at the CV. CV is 1.67. CV 1.67. Okay, next is SC equal to standard deviation of the sample. So standard deviation of the sample at S divided by SQRT 49. So you get SC. SC. SC is this, right? SC is this. Then your X bar is X bar is here. X bar is here. X bar is here, 107, then plus C minus 1 plus 1, then times ME. Oh, okay, ME. I haven't write ME here. ME is here. Copy and ME. I'll have ME. X bar is this 102 to 113. Okay, so this is the entire formula. Put them into together. So lower bound is X bar minus the standard error here. Standard error times the critical value using t-distribution. Okay, critical value using t-distribution. Run it. Okay, so the result is the same. Okay, so there's a trick here. You can obtain the same answer simply by using t-test. Okay, so like a t-test. If you type t-test this value, then set confidence level to 0.09, you can get a 90% confidence interval straightforward. Okay, so yeah, if you are sure this is a t-test, you can use t-distribution of to calculate confidence interval, you can use this method. Then run, have a look at the t-test helper function. So t-test, 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 and a few examples. So t-test, t dot test. You can have x equal to something. Okay, x equal to this entire thing. Then run it. Now by default, it gives you a 95% confidence. Okay. By default, then I can set a different confidence level. So confidence level, you tap. Then what can you key in? 0.95. Okay, give you 95. You want 0.99, they give you 0.99 confidence interval. You want 0.90, give you 0.90. You want 0.8, you give you 0.8. Okay. Okay. What about you want a 0.05? 0.05 is very narrow, okay? 0.01, 0.01, okay? It's also very narrow. Have you ever tried 0.0? Okay, I want 0% of confidence. What will happen? It give you a point estimation, which is exactly the mean value. Okay, you take note of it. I want 0% of confidence, then it give you a point estimation. Now, earlier we mentioned, right, for continuous random variable, if you give a point estimation of the mean value, what is the probability for you to get correct? Or that means the sample mean is exact the same as the population mean. The chance is zero because it's continuous random variable. So point estimation will give you zero probability. Then what about confidence interval? 100. You want one error in t-test. So confidence level must be a single value between 0 and 1. In general, it's actually positive infinite to negative infinite. It cannot be calculated. What about 99.9999? 99? Oh, okay. 0.99. Okay, 0.99999. Yeah, it's still quite give you a quite reasonable large range, unless you want to go to 100%. 1%. Okay, the confidence interval 1. Okay, when your confidence interval level is 1 or 100%, it give you a negative infinite or positive infinite. Yes, right. It's correct. Okay. Okay, 3.2. Oh yeah, the confidence level, you're only keeping a value from 0 to 1, no more than 1. Next is 3.2. Okay, consider sample of the newborn chicken time equal to 0. Then we define RV. Then the newborn chick build a 95% interval of the light on newborn chicks mu 0. Okay, directly use t-test. So the key thing is you make sure that you get the time correct. So this is one way. Okay, another way is you use this one here. Remove the you have the data set, then you put a condition in the square bracket left to the comma, then it'll give you all those columns, weight, time, check diet. Okay, right? Then you add the dollar weight, then it give you the weight of them. Then after that, you can do a t-test. Do a t-test, t.t test. Then you type x equal to this one, then you want a confidence level, this is 0.95. Then they give you average of 41.06 gram, then plus minus a margin of error will give you this 95% confidence interval. Okay, good. High confidence interval. Yeah. Okay, confidence interval. Okay, question 4. Question 4. Question 4. Okay, give me one moment now. Okay, question 4. The condition is, okay, question 4. Suppose from random sample normally is with unknown mean value and known variance. Okay, known variance and normally distributed. So that's a z distribution. How large must a random sample be? And we're finding the n so that 95% confidence interval with a total length lesser than 0.01 sigma mu. The confidence interval of a total length less than 0.01 sigma. Okay. So the total length of a CI is this, right? So it is 2 times margin of error. The length is 2 times the margin of error. Remember that. So the confidence interval is centered at x bar, then plus minus the margin of error. So the total length of the confidence interval is 2 margin of error. 2 margin of error is 2 times critical value times standard error. Okay, it's here. That's why I said 2 times the critical value times the standard error. Okay, so that's quite straightforward. Then this one is equal to 0.01 sigma. So you cancel 2 sigma. In the end, you will be able to get the square root of n. Then you get the n. Okay, so that's question 4. Okay, so the confidence is this. Only that means m is greater than how much? Okay, so 2q norm 0.975. So we want to achieve 95% confidence interval, then the q norm 0.975, and this one divided by square root of n is less or equal to 0.01. We just time the equal to 0.01. Then you do you continue the 200 times 100 each 200, then move this one here, square root and end here. Then n is greater than this value. Okay, n is greater than this value. Then n greater than this value. Let's run it. It's 1.553.658. You run up, so 5.9. Okay, so that's the sample size that you want to achieve. Okay, n. So this is n. This is n, right? This is n equal to this one, equal n is actually greater than this one. Okay, so n equal to this one plus round up. So 153.659. 659. Yes, right. Question 5. An analyst would like to construct 95 confidence interval for the mean stock price in 2 industry. Industry, high-risk industry with a known population standard deviation of $20, whereas industry low risk with a known population standard deviation of these. What is the minimum sample size required by the analyst if you want to restrict absolute error at $5 for industry A? Okay, $5 for industry A. The restrict the absolute error. Okay, so that means margin of error. Margin of error is equal to Z, the critical value times standard error, to be $5. So okay, so we just calculate. And they want to be how much confidence? 95% confidence. Okay, so 95% confidence is 0.975 times this one less than 5. So this one is n greater than this value. Okay, so round up to 66. So just run it. Yeah, 66. Okay. Then if you are calculating the absolute error is $5 or $5, the total range is 10. So that's with 2 times of the margin of the error. Okay. Error. Then I'll put all the sigma into it. 20.6 is the sigma there. 20.6 is the industry A's standard deviation. Okay, good. Then 5.2, what is the minimum samples required? And if you want to restrict the average for industry B, okay, industry B is this. The only difference is the standard deviation are different. So industry B standard deviation is smaller. Okay, if industry B standard deviation is smaller, then the number of sample size required will be smaller to have the same margin of error. So with higher standard deviation, industry A requires a larger sample size to achieve the same absolute error. Okay, so that's question to university first. Because original industry have high risk, more volatilities, more uncertainties in order to the naturally has more uncertainty in order to restrict to a error to be smaller. When the population varies a lot, then you need more sample size. That's not that. That's quite natural. Okay. So question 6. Consider the file OW7 question which contains a test score of 149 students. Load the file into a calculator for the mean test score and compare. Okay, we do it one by one. So first, 6.1, we need to read the CSV, right? So read the CSV first. Find your W7 question 7. Okay, let's open it. Okay, so this is the data. Oh, score. There are only score, one column score. So 149 students. So with 1 decimal places. Okay, these are the score. So let's have a look at the histogram. Oh, this score is left skewed, right skewed. It is left skewed. It is left skewed. That means there will be lesser extreme values. So you see lower than 40, that's a failed. So failed case is actually quite extreme. So much lesser extremely low scores. So the sample size, this one, would you use either lens command or view to find out? Okay, so the sample size is 14910. And then ENGTH type this. Let's verify it. In fact, you can find it from here, 149 observations, 149 observations. That's a convenience of using RStudio. So it is have a lot of windows for you to observe. Okay, so confidence interval, again, margin of error, or CV times SC, right? CV times SC, so your CV first is, you use which distribution? Okay, first, this is a sample. Okay, you do not know the population standard deviation. You only have a sample of 149 students. So it is not a population. So population standard deviation not known. Then you go there. Is the population normally distributed? Actually, it's not. Even without viewing it, and you are not aware, the question didn't tell you, so it is assumed to be not normal. So if it's not normal, it did a sample size greater than 30, then 149 greater than 30, use t distribution. Okay, use t distribution. So QT, what? QT, then probability, 95% confidence, 1 minus 0.05, no, 0.25, which is, in fact, there is a universal method shown on the slide, divided by 2. So this is the 1, then you use 1 minus it. 1 minus 1 minus 0.9. Yeah. 0.95 is 0.05. 0.05 divided by 2 is 0.025. Then 1 minus it. Then degree of freedom is sample size n. Do we have a sample size n? Let's do this. N equal to this. Then let's display n. N is 149. Okay, let's do 149 minus 1 instead of using n. So CV. So we can find CV here 1.97. 1.97. Then what about SC? SC is the, oh, we do not have the standard deviation of the sample. So we need to find the standard deviation of the sample. We need to use the SD function. SD function of this data. Let's have a look. SD, okay, let's look at SD first. 10. Then you need to divide by SQRT to get the standard error. Sample size 149. 149. Okay. So standard error is this. Standard error is the standard deviation of the sampling distribution, 0.083. So the sampling distribution is in your imagination because at the meantime, we only have one sample of 149 students. One sample mean. So margin of error has been calculated 1.6. So now, yeah. So what is the mean value? Mean value is this. Then X bar is this. X bar 70 plus C minus 1 times ME. So this is again manual calculation. So it is this one, right? So 68.58. Upper limit is 71. Okay, upper bound. So this is upper bound. This is a lower bound. Okay, this is upper bound and lower bound. Right. So this is a calculation in one line, but I have breakdown for you. So you can also use a t-test, filling the score, 149 scores, set the confidence interval to be 0.95. You check, verify whether these two are the same. Yeah, these two are the same. Okay. Yeah, these two are the same. These two are the same. Okay, good. Right. So this is question 5. Okay, question 5. Okay, compare 95 with 99 if 99 is longer or shorter than. Okay, so we can do this. This is 90, 95 we already have. This is 95. Okay, 95. This is 95. Okay, so this is 95. You want 99, you can use T distribution, but for me, I do this 99. If you want 99, then you change 95 to 99, run everything again. Your critical value changes, then standard error doesn't change, margin error will change, then the mean value plus minus. So you want a 99% confidence, you are noticing this confidence interval range gets slightly wider, okay? You want to be more confident, you need to extend to two sides of the sampling distribution so that area under the curve in the middle are larger from 95 to 99. So inevitably, the interval gets larger, get wider, okay? So you can also use a t-test, okay, to give you the same result. Okay, they give you the same result. You can notice this one and this one are the same, this one and this one are the same. Okay, so same as manual calculation. 6.2, oh yeah, 6.2 I mentioned, yes, larger. Then 6.3, we collect data from another 150. How will this larger sample affect the total length of 159C? I suppose the sample standard deviation under the larger sample is similar to the original one. Okay, so a larger sample would make the CN narrower. This is good for a given probability in the case that we would prefer a more precise estimate error. We can have this by increasing the sample size. Yes, overall, you increase the sample. Basically, you add this 150 student to the existing 149. So your sample size become larger. Then your standard error reduce. So standard error is the standard deviation of the sample, which doesn't change that much. It was mentioning that it doesn't change that much. Then divide by square root of n. So the n becomes larger, almost doubled. Then square root of it is become larger. So yeah. So then your standard error gets smaller. So your standard error gets smaller. Your critical value has been unchanged. So your margin of error gets smaller. Your margin of error gets smaller. Your X bar plus minus a smaller value than the confidence interval range gets smaller. Okay. So that's the recap. Okay. So that's a recap here. Yeah. So your margin of error gets smaller. Then yeah, your confidence interval also gets smaller. Okay, so that's all for today. Great. That's all for today. Bye bye.